So this reaction is Friedel acylation and involves the addition of an acyl group onto the benzene ring as seen here. The acyl group does not just have to be this ketone group here. It could be any of the following, like this, or it could contain a nitrogen like this, or it could even have an alcohol like this. So in this reaction, the benzene ring is going to act as a nucleophile. It's because the benzene has delocalized pi electrons, and it's also very stable due to its resonance, as it's an aromatic compound, as you can see here. So if the benzene is a nucleophile in this reaction, that means the psyllium, the acyl group, would have to be the electrophile. So for this reaction, the electrophile would be an psyllium ion, as seen here. So in order to generate this, we're going to use the acid chloride, and we're going to treat it with the lowest base, AlCl3. And this reaction is going to be like a nucleophilic attack here, and we're going to get this intermediate right here. But this intermediate is not very stable because of the positive charge on the chlorine. So the acyl group is actually going to end up kicking off the chlorine. So we're going to generate an psyllium ion plus AlCl4. Alright, so now that we have our nucleophile benzene and our electrophile the psyllium ion, the reaction can continue. So the first step is going to be a nucleophilic attack from the benzene ring to the carbon cation. And this is going to cause the benzene to lose aromaticity. So this is going to be the rate determinant step of the reaction, as it will require an input of energy. As you see, this is the intermediate we have, but this intermediate is also resonance stabilized, as seen here. So there's actually 3 forms for it, and that would be called the sigma complex for this. And you see here, all these 3 intermediates represent the sigma complex of this reaction. So the last step for this reaction is for this intermediate to regain its aromaticity. And this can happen from any of the sigma complexes, but I just chose this one right here. So this will happen from the use of the AlCl4 we generated when making the psyllium ion. And the electrons from the chlorine aluminum bond are going to take this hydrogen, and this is going to put the double bond back into the ring. So what we're going to generate is another aromatic compound with our acyl group and hydrochloric acid and AlCl3. So this would represent the reaction coordinate for this reaction. This would represent the benzene ring, which is obviously very stable, so it'll be lower in energy. And this right here represents the first step in the reaction, which is a nucleophilic attack of the psyllium ion. This represents our transition state right here. And as you can see, the sigma complex can stabilize that step as it is lower in energy. And then the last step was to re-aromatize the ring to generate an overall more stable product.